calculate this V error term at the end of by 2 phase. Yeah, at the end of by 2 phase, yeah, this ratio are the same. Okay, then let's just see. Oh, sorry. This should be here, right? This is connected to that. Okay, what's the Vx value here? Oh, let's just see. So, initially, in the preceding by 1 phase, this charge was 0, right? It was 0. No, this charge was 0, 2. But during by 2 phase, it got some value, Vx value, right? Vx value. So, let's just see. This is charge transfer. What is this charge during by 1 phase? Do I need that by 1 phase value? Oh yeah, this is difficult to derive equations, some equations. Okay, let's just see. Let's separate the offset error and the gain error in 2 stages. So we have input offset voltage, and then for the first case, I don't have a gain error. Okay, my gain A is infinite. Okay, then how does offset error is compensated by CDS? Let's look at it. Yeah. So because A equal infinite, there is a negative feedback by C2 prime. My Vx should be EON, right? Virtual ground, okay. Virtual ground. Because A is infinite and there is a negative feedback. So my those C1, C2, and all those things will sample. I assume my input is 0. All those things will sample those input offset voltages. Okay, so my C1 will charge C1 EON. This will be charged to C2 EON, something like that. Okay. So during next by 1 phase, this path is isolated, so it's connected to V in. Oh, sorry, there should be EON there. EON. VO prime. This is VO. Yeah. Oh, actually, do I need a V in there? Input offset voltage. Here, there is a V in here. Oh, okay. C1, C2 is V in. Actually, that doesn't matter. Okay. So because A is infinite, so it doesn't matter. C1 charge will be during by 2 phase. C1 prime will be charged EON minus V in. This charge will be charged to EON minus VO prime or something. Okay, but anyway, C1, C2 will be charged to this EON voltage. Okay. So initially, at the start of by1, the charge here was C1 EON. Okay. The charge there was C2 EON. Now there is a negative charge there. Yeah, at the end of see, for this path during by1 phase, there is no DC path for this cassette. So sum of charges on inside this cassette must remain the same. So initially, the sum of charge inside that cassette is this one. At the end of by 2 phase, those charges will be redistributed. Then, you know, this charge must be EON, C1 EON minus V in, right? Because of V in there. At the end of by 1 page, this charge must be C2 EON minus VO, right? Okay. So this charge will be EON minus V in. That charge is C2 EON. Is it C plus? Oh yeah. Sorry, should be positive. Eh? Oh, how come? How come there is a negative? Oh, that's okay. The different notation. Sum of charges inside this one is EON, right? Yeah, this C2 EON minus VO. If my EON changes very slowly, yeah, I have just a simple. So it's independent of EON, right? So I can compensate for input offset voltage. Question? No? Yeah, let's move on the gain error. Second case. Say I assume input offset voltage is 0. I assume my gain is small. Okay? We just separate the issues.
저기 하이2 페이지에서 아래쪽에 있는 게 V나 VX로 해가지고 차지돼 있잖아요. 프라임에 있는 게. 근데 이게 파이원 페이지 됐을 때 이쪽은 VX 그 노드가 EON인데 이거 V 있는 얘는 안 물려 있으면은 CO 프라임하고 C2 프라임에 있는 차지는 어디 그거는
Okay, the question is, see, during by 2 phase here, this C1 will be charged to some EON minus V in. This charge will be charged to EON minus VO prime. Yeah, then this charge is, I mean, during the following by 2 page, this path is just cut. Then, you know, there is just this path, right, during by 1. Yeah, they are completely discharged to 0. So actually, this charge, those charges C1 prime and C2 prime are isolated from this cassette. So there is no charge transfer in between them. Okay, any other question? Okay, let's look at the second case. Just gain error, no offset. Yeah, I have a V in here. So it's by 1 there, and by 2 there. So I have a C1 pass here, and then I have a, so my offset is a 0. My gain is a small. Okay, so here see, let's see, how can I calculate this Vx at the end of by 2 base? Okay, let's see. Yeah, during by 1 base, yeah, by 1 base. Yeah, they are completely discharged to 0 by 1 base. Eh? Yeah, that by 1 base. Okay, they have some charge here. They have, let's see, what's the charge on C1? C1 is V in minus Vx or something like that. So this charge will be, at the end of by 2 base, you know, the charge there is C1 Vx minus V in. The charge here is C2 Vx minus Vo. Okay. And then, yeah, this is by 1 base, right? By 1 base, this charge is 0, 0, and that charge is something. Yeah, during by 2 base, what happens? I mean, following by 2 base. Let's draw the circuit again. See, I have a V in on the bottom pass, connected C1 prime, and then say it's connected to op-amp, minus input node. This is my Vx, and then this is connected to here. Then see, I have those capacitors, C2 capacitor and C1 capacitor. So here again, we have a cassette. Yeah, in this cassette, there is no DC current pass. So charge inside this cassette must remain the same during by 2 base, right? During by 2 base. The sum of charge inside this cassette is just sum of those two, because this is only 0 at the start of this by 2 base, right? Okay, so my sum of charge is C1 Vx minus V in plus C2, is it plus? Oh yeah, it's a plus. Vx minus Vo prime equal, yeah, at the end of by 2 base, what happens? Yeah, at the end of by 2 base, this V in, so I assume V in is very slowly varying. I assume my Vx is the same during by 2 and by 1, okay? For simplicity. Yeah, and then what's this charge here? Yeah, this charge is C, for this C1, let's see, for this C1, it's just C1 Vx, right? Because this is Vx. C2, yeah, that's C2 Vx, right? And how about the C1 prime? Yeah, C1 prime is C1 prime Vx minus V in. How about the C2 prime? Yeah, that's C2 prime Vx minus Vo prime. Okay. Yeah, then what happens? Let's see. C1, C2 Vx. Are they the same? C1 Vx. Oh, yeah. They are here. They have the same ratio. Let's see, Vx minus Vo. So, yeah, the ratio is set to same. The values are not the same, C1 and C2. Yeah, you can calculate the Vx here, right? Let's try to calculate the Vx here. See, if I collect all those Vx's, what do I have? Oh yeah, they are gone. Right? This disappears. Let's see, this disappears. And then, is it right? Yeah. Let's try to calculate it. Okay. Then how can I calculate Vx? This Vx thing is, my Vx is what? Oh yeah. C1 prime C2, C1 prime C2, and then what else? C1. Oh, it's V in, C1 minus Cx V in, C2 minus Cx Vo. Okay. Is this minus? Yeah. Minus V in, minus Vo. Oh, something wrong, right? Something wrong. C1, C2. Okay, this is wrong. Okay, let me write it again. Yeah, this is C2. This numerator is wrong. Minus V in, then C2 minus CO. Okay. Is this minus? Something like that, okay? Something like that. So let's see, but I don't have a gain error yet, right? So actually, let's see, what's the gain error? Did I use a gain error equation here? So this voltage should be the gain error. My Vx should be the gain error, right? So I must equate my Vx. Where is my Vx equation? Here. So this Vx equation should be that Vo prime A or something like that. Then can I write something here? Vo prime? Pretty complex, right? Pretty complex. So I can write the Vx in terms of some function of V in. Then say you can find out whether this one compensates the gain error or not. Pretty complex. But if you follow the equations, This is pretty complex. Yeah, all those equations are based on the sum of charge inside the cut set. Does not change during each phase if it's not connected to outside the world by DC path. So anyway, so we can derive equations here. Okay, let's believe this equation. My VO is this desired term. Then this gain error term is reduced to small. The conventional gain error term is this. The conventional gain error term looks like that. However, I have a square here. Okay, so it reduced significantly. And also, input offset term is, yeah, it's not complete. But if gain A is pretty large, see, actually this doesn't matter too much. Just one away. Okay. So this CDS can suppress gain error by this 1 over A squared term, and also this EON is not completely disappeared, but reduced by 1 over A. Question? No? Yeah, this EOS works pretty well. Okay.